Since the dawn of the space age, humanity has dreamed of living and working beyond Earth. The Moon, our closest celestial neighbor, has always been the first stepping stone. But to live there, to truly stay, requires something more than courage. It requires power, reliable, continuous, life-sustaining power. And now, the United States, in partnership with NASA, is preparing to bring an energy source once confined to Earth's reactors to the lunar surface. Today, we're diving into the science and the strategy behind building the first ever nuclear power plant off Earth. This is the story of America's bold plan to build a nuclear reactor on the Moon. On Earth, we take electricity for granted. Our homes, our cities, our industries all run on a vast and interconnected grid. But on the Moon, there is no such lifeline. Solar panels work, at least part of the time. But the Moon has a problem. Its day and night cycle lasts nearly 29 Earth days. That means 14 days of sunlight, followed by 14 days of darkness. In the lunar night, temperatures plummet to nearly minus 250 degrees Fahrenheit. Without power, astronauts and equipment would freeze. Batteries alone can't sustain a base for 2 weeks. Solar alone isn't enough. NASA needs an answer. And the answer may lie in the atom. The idea of nuclear power in space isn't new. In fact, it dates back to the Cold War. During the 1960s, the United States developed small nuclear reactors under a program called SNAP, the Systems for Nuclear Auxiliary Power. In 1965, SNAP-10A became the first and only nuclear reactor the U.S. ever launched into space. It operated successfully for 43 days before a voltage regulator failed. But smaller nuclear devices, known as radioisotope thermoelectric generators, or RTGs, have powered spacecraft for decades. From the Apollo missions, which carried nuclear-powered seismometers to the Moon, to the Voyager probes now traveling beyond our solar system, RTGs have provided quiet, steady electricity where sunlight is scarce. The next step is bigger, not just generating watts, but kilowatts, or even megawatts, enough to power a human settlement. NASA calls it fission surface power, a compact nuclear reactor designed to run on the Moon for at least a decade. The goal: provide a steady supply of at least 40 kilowatts of electricity. That's enough to power about 30 average homes on Earth, or more importantly, to run a lunar habitat, recharge rovers, support scientific labs, and keep life support systems running. Unlike massive reactors on Earth, these are small, modular units. Each could fit inside a lander, be lowered to the surface, and begin producing power almost immediately. In 2022, NASA awarded contracts to 3 companies, Lockheed Martin, Westinghouse, and IX, to design concepts for these lunar reactors. Their challenge: make nuclear safe, portable, and reliable in one of the harshest environments imaginable. So how does it work? At its heart, a lunar reactor uses uranium fuel, just like on Earth. Inside the core, atoms split in a process called fission, releasing heat. That heat is transferred through a system of pipes and coolants, then converted into electricity, using technologies like Stirling engines or advanced turbines. Unlike chemical batteries or solar panels, nuclear doesn't depend on sunlight, weather, or day-night cycles. It runs continuously, day after day, year after year. And the design emphasizes safety. These aren't giant, sprawling power plants. They're compact, sealed systems, engineered to be fail-safe, to shut down passively if something goes wrong. NASA's Artemis program aims to return astronauts to the Moon this decade. The long-term vision is not just flags and footprints, but a sustainable presence, a base camp, a gateway for Mars. To build that future, power is as essential as oxygen and water. Solar can support some operations. Fuel cells can bridge short gaps. But for permanence, for industry, for science that runs through the long lunar night, nuclear is the only option. But nuclear power is never without controversy. Critics raise concerns about safety. What happens if a launch carrying uranium fails? Could radioactive material spread in Earth's atmosphere? NASA counters that the fuel would be in a safe, non-reactive form at launch, incapable of starting a chain reaction until properly assembled on the Moon. Others question cost. Developing, testing, and certifying space-rated nuclear reactors is enormously expensive, but proponents argue that the payoff, true energy independence on the Moon, is worth the investment. And beyond cost and risk lies another challenge: public perception. For many, the word nuclear still conjures memories of Chernobyl, Fukushima, and Cold War weapons. NASA must show that space nuclear power is something very different: small, clean, and vital for exploration. Imagine the year 2040. On the rim of a lunar crater, a cluster of habitats glows in the darkness. Inside, astronauts, and perhaps settlers, live and work. Greenhouses grow food under artificial light. Rovers venture far across the surface, mapping, mining, exploring. All of it powered by the steady heartbeat of a compact nuclear reactor. From this base, humanity prepares for the next great leap to Mars and beyond. And the lessons learned on the Moon, how to generate, distribute, and live with nuclear power in space, become the foundation for interplanetary civilization. For centuries, the Moon was a distant light in the night sky. Today, it is becoming a frontier once more. As America and NASA take the bold step of bringing nuclear power to the lunar surface, they carry forward a vision first kindled in the 20th century: that humanity's future lies not just on Earth, but in the stars. The challenge is immense. The risks are real. But the rewards, limitless. This is not just about the Moon. This is about learning to live beyond Earth, powered by the atom, driven by curiosity, and guided by the unshakable human will to explore. The United States is building the future of space. And on the Moon, the lights will never go out. So let's keep asking, why, on YouTube?